Far across the cosmos, at a distance of 13 billion light-years, scientists have found objects that fundamentally challenge our cosmic narrative. They have identified galaxies of such immense size and intricate structure that they seem to be more ancient than the cosmos that contains them. These galactic behemoths, shining like celestial cities in the void, possess a number of stars comparable to our own Milky Way. Yet they emerged when the universe was thought to be a mere fledgling, just 500 million years into its existence. We are about to explore the incredible findings that are rattling the very pillars of science. Look at galaxies that seem to ignore the known laws of physics, and consider new theories that could potentially double the age of the universe. The James Webb Space Telescope has done more than alter our view of the cosmos. It may have completely upended our most deeply held beliefs about the nature of reality. The date of July 11th, 2022, marked a monumental turning point. Researchers across the globe began receiving the initial images from the James Webb Space Telescope, anticipating views of the universe in its infancy. What they discovered instead were titans. Dr. Erica Nelson gazed at her monitor, unable to believe what she was seeing. A minuscule red speck she was examining ought to have been a hazy, indistinct blur, a primitive galaxy just beginning to kindle its first stars. Yet the figures generated by her analysis were so startling she almost dropped her coffee. Its distance was calculated at 131 billion light-years, and its mass was equivalent to 100 billion suns. This galaxy was as star-rich as the Milky Way, but it existed when the universe was just 700 million years old. It was the celestial equivalent of discovering a mature oak tree standing in a field of freshly planted saplings. Based on our current understanding of galactic evolution, this finding should simply not be possible. The Big Bang model posits that after the universe's birth 138 billion years ago, it took several hundred million years for the first stars to even ignite. Those stars then needed to complete their life cycles and explode, dispersing heavy elements into space for future stellar generations. Constructing a galaxy on the scale of our own should require billions of years of this cosmic give and take. But this galaxy seemed to have bypassed that entire developmental sequence. It shone with the light of mature stars, displayed sophisticated structures, and possessed heavy elements that shouldn't have been present yet. This finding contradicted the established timeline of cosmic history. If the universe was only 700 million years old at that point, how did this galaxy gather the time to become so enormous? The ramifications sent tremors through the scientific establishment. It suggested that either our theories of galaxy formation were deeply flawed, or the age of the universe itself was far greater than we have assumed. Some scientists started to voice a radical notion. The Big Bang theory itself might require a fundamental reevaluation. Dr. Nelson and her team had uncovered what is now termed the impossible early galaxy problem. In the ensuing months, more such discoveries began to populate the view. Every new observation only added to the puzzle, questioning the very tenets of contemporary cosmology. That lone red speck was merely the first piece of a cosmic enigma that would lead humanity to re-examine all it presumed to know about the universe's origins. The cosmos was thought to run on a strict, unbreakable schedule. The Big Bang model dictates that the initial 400,000 years were a primordial inferno, a sweltering, thick soup where even atoms could not coalesce. It was only after this haze lifted that hydrogen and helium atoms could form. For another 100 million years, these basic elements drifted until gravity drew them into the first star-forming nebulae. Those initial stars, gigantic and fleeting, had to detonate as supernovae to forge heavier elements like carbon and oxygen. Only after that could a new generation of stars begin to shape the intricate galaxies we observe in the present day. This entire progression should demand at least 1 billion years, analogous to constructing a skyscraper. You lay a foundation, erect a steel frame, add floors, and then apply the final details. The universe was believed to have adhered to this methodical building plan. Yet the galaxies Webb found seem to have finished their construction in less than half the expected time. They are filled with heavy elements that should be absent, stars that should not have yet formed, and structures that should not have had the opportunity to organize. It is akin to a magnificent cathedral being erected in a single day. The timeline does not compute. If the universe started 138 billion years ago, and we are viewing these galaxies as they were 131 billion years ago, it leaves a mere 700 million years for their creation. Current physics dictates they would require a minimum of 2 billion years to achieve such colossal proportions. This temporal discrepancy has led astronomers to weigh three possibilities, each one more groundbreaking than the one before. First, that galaxy formation operates in a completely different way, with stars forming at a rate 100 times faster than our models suggest. Second, that the universe is significantly older than 138 billion years, which would grant these galaxies the necessary time to develop. Third, that the Big Bang theory itself has a fundamental flaw. The cosmic timepiece is running, and its hands don't align with the schedule we thought was inscribed in the heavens. Among the myriad galaxies captured by Webb, a particular type emerged like warning beacons in the cosmic twilight. Astronomers named them little red dots due to their appearance as minute crimson points of light, entirely undetectable by earlier observatories. These red dots became the crucial evidence in cosmology's most profound puzzle. In contrast to typical galaxies that radiate light across a wide spectrum, these objects emitted an intense glow in infrared light, while being almost invisible at other wavelengths. This pronounced redness indicated they held something remarkable, perhaps ancient stars or supermassive black holes actively consuming matter. Upon analyzing the first red dot, researchers found it contained approximately 100 billion stars, placing it on par with our Milky Way's mass. However, this galaxy was present when the universe was only at 5% of its current age. The observation was like encountering a fully developed adult in a maternity ward. The red hue itself presented a narrative that defied our understanding of early cosmic development. In a young universe, galaxies are expected to be blue and brilliant, teeming with hot, massive stars that burn out rapidly. Red galaxies are usually a sign of an old, established stellar population, composed of stars that have been shining steadily for eons. Yet these red dots seem to be paradoxically both young and ancient. They existed in the early cosmos, but showed the stellar characteristics of old systems. This contradiction was like finding a blizzard in the middle of July. It went against the core principles of cosmic evolution. As Webb's images revealed more of these red dots, the trend became undeniable. They weren't just scattered exceptions, but a significant population of massive early galaxies. Some projections indicated there were 100 times more of these objects than the Big Bang model could account for. The scientific world began to factionalize. One group contended that the red dots were proof that galaxy formation in the early universe was vastly more efficient than previously conceived. Another proposed they were optical illusions generated by supermassive black holes that were outshining their host galaxies. But an increasing number of scientists started to entertain a more profound idea, that the red dots were signaling a fundamental error in our understanding of the universe itself. Within every galaxy, stars are born from immense clouds of gas and dust through a process that typically spans millions of years. However, the gigantic early galaxies found by Webb appear to have drastically shortened this timeline to an almost unbelievable degree. To build a galaxy of 100 billion stars in a mere 700 million years, star formation would have to proceed at a velocity that contradicts known physics. Contemporary models indicate that under ideal circumstances, galaxies can only transform about 10% of their gas reserves into stars. The remainder is expelled by powerful stellar winds and supernova shockwaves. Yet these ancient giants seem to have reached conversion efficiencies close to 100%. It would mean that nearly every atom of hydrogen and helium was converted into a star with minimal waste. The energy required for such a feat alone is staggering. As massive stars take shape, they produce potent stellar winds that heat the surrounding gas to millions of degrees. This superheated gas typically disperses from a galaxy, halting further star formation. It's a cosmic regulatory system, controlling the rate of new star birth. For these early galaxies to create so many stars so rapidly, they must have found a way to bypass this natural cooling mechanism. Some theories suggest the early universe's higher density made it more difficult for hot gas to escape. Others propose that dark matter behaved differently in the primordial cosmos, creating more powerful gravitational anchors to hold onto star-forming material. The mathematics behind such rapid star formation stretch the limits of theoretical physics. Computer simulations attempting to model these conditions either couldn't generate enough stars or produce galaxies that should have been ripped apart by their own internal energy. Still, the observational proof was irrefutable. These galaxies had somehow managed star formation rates that modern physics deems impossible, condensing billions of years of cosmic history into a few hundred million, like viewing a time-lapsed film of galactic growth. The consequences went far beyond astronomy, implying that our grasp of the universe's fundamental workings might require a complete overhaul. At the center of each massive galaxy lurks a supermassive black hole, a gravitational leviathan with a mass millions or billions of times that of our Sun. In the early universe, however, these cosmic behemoths pose an even deeper puzzle than the galaxies they inhabit. The red dots observed by Webb not only contain an impossible quantity of stars, but also harbor black holes that should not have had time to form. These objects exhibit signs of actively accreting black holes, with gas spiraling into them at incredible speeds and reaching temperatures of millions of degrees. This process results in quasars, some of the most luminous objects in the cosmos. But cultivating a supermassive black hole is a time-consuming affair, like nourishing a cosmic beast with an insatiable appetite. A black hole must pull in matter from its environment, and there are physical constraints on how quickly it can do so. This is known as the Eddington limit, the highest rate at which matter can fall into a black hole before the outward force from the heated gas counteracts the inward pull of gravity. Even if a black hole were to feed at this maximum rate continuously, it would require hundreds of millions of years to grow from a star-sized seed to supermassive status. Yet the black holes Webb has found seem to have accomplished this growth in just a fraction of the available time. Some appear to have been accreting matter at 5 times the Eddington limit throughout their entire existence. This is akin to finding a person who gained 1,000 pounds while eating only a single meal a day. The physics just doesn't permit it. Nevertheless, these primordial black holes seem to have defied the very laws that should govern their expansion. The enigma deepens when you consider their origin. The conventional theory is that they originated from the collapse of the very first massive stars. But those stars would need time to form, live out their lives, and then die before leaving behind black hole remnants. In the early universe, this process alone would use up most of the available time, leaving very little room for subsequent growth. Some scientists now suggest that supermassive black holes could have formed directly from the collapse of ancient gas clouds, foregoing the stellar stage altogether. Others theorize that the early universe was seeded with enigmatic objects known as primordial black holes, which served as the kernels for later growth. But these cosmic monsters were on the verge of unveiling an even more astonishing secret about the fabric of reality itself. What if the most colossal galaxies Webb has seen aren't colossal at all, but are instead cosmic conjurers creating the grandest of illusions? New studies propose that some of these early giants could be optical mirages generated by the very black holes at their cores. As matter descends into a supermassive black hole, it creates a swirling vortex, known as an accretion disk. Friction inside this disk heats the material to millions of degrees, making it shine more brilliantly than billions of stars combined. This overpowering radiation can eclipse the entire galaxy around the black hole, giving a false sense of immense stellar mass. The phenomenon is like trying to count the candles on a cake while someone points a spotlight directly at you. The blinding light makes it impossible to discern what's really there. In a similar fashion, actively feeding black holes can obscure the true stellar population of their host galaxies, causing them to look much larger than they are. This finding presented a possible resolution to the impossible early galaxy dilemma. If a significant number of the red dots were, in fact, moderately sized galaxies with exceptionally luminous central black holes, the crisis in cosmology might be averted. The universe wouldn't have to defy physical laws to produce massive galaxies in record time. However, this explanation introduced its own set of complications. Even if the galaxies were smaller than they seemed, they still housed supermassive black holes that shouldn't exist so early in the universe. The mirage theory simply transferred the impossibility from the stars to the black holes. Moreover, detailed studies of some red dots revealed clear evidence of substantial stellar populations coexisting with the black hole signatures. These galaxies weren't merely bright. They were genuinely enormous, containing billions of stars that had somehow formed in the blink of a cosmic eye. The mirage effect could perhaps account for some of Webb's findings, but not all of them. Many of the early galaxies appeared to be both massive and luminous, indicating that the universe had indeed found a way to fast-forward cosmic evolution beyond our current comprehension. As astronomers tried to distinguish authentic giants from cosmic deceptions, an even more radical notion started to surface from the annals of scientific history. In 1929, as Edwin Hubble was discovering that faraway galaxies seemed to be speeding away from us, a Swiss astronomer named Fritz Zwicky suggested a profoundly different interpretation of the same data. He wondered if the galaxies weren't moving at all, but rather if light itself was transforming during its journey through space. Zwicky's concept, known as tired light, proposed that photons progressively lose energy as they traverse the vastness of the cosmos. As light's energy diminishes, its wavelength lengthens, causing a shift towards the red part of the spectrum. This redshift would create the illusion that distant galaxies are receding when they are, in fact, stationary within a static universe. The tired light hypothesis presented a graceful alternative to the prevailing model of an expanding cosmos. Rather than space itself expanding and pulling galaxies along, the universe would be eternal and unchanging. The observed redshift would simply be a natural byproduct of light aging over its billion-year voyage to our instruments. For many years, tired light theory was relegated to the periphery of cosmology, rejected by the majority of scientists because of several observational inconsistencies. The theory failed to explain why distant galaxies look smaller than they should in a non-expanding universe. It also couldn't account for the cosmic microwave background radiation, which permeates the entirety of space. However, the discoveries from the James Webb Telescope have injected new vitality into this long-dormant theory. If the universe isn't expanding, then distant galaxies are not actually young. We are seeing them at their real age, which could be billions of years older than the Big Bang model allows. This would grant the necessary time for massive galaxies to develop without contradicting the laws of physics. More recent investigations have sought to merge the tired light concept with subtle shifts in fundamental physical constants over cosmic time. This hybrid framework suggests the universe might be 267 billion years old, almost double the age estimated by Big Bang cosmology. In this more ancient cosmos, even the most remote galaxies would have had ample time to assemble their enormous stellar populations. The revival of tired light is more than just a competing theory. It questions the very essence of modern cosmology and our conception of time itself. What if the fundamental constants of physics, the fixed values that dictate the behavior of matter and energy, were not constant after all? Recent investigations suggest that the speed of light, the force of gravity, and other supposedly immutable parameters could have been different in the universe's early stages. This revolutionary concept arose from efforts to harmonize Webb's impossible galaxies with established physical laws. If these fundamental constants were not fixed, the early universe might have followed a different set of rules than it does today. Stars might have formed more quickly, black holes could have grown at a faster rate, and galaxies might have come together in a fraction of the time we once thought was required. The notion of varying constants is not entirely foreign to physics. Certain theories of quantum gravity propose that fundamental parameters could change as the universe expands and cools. But integrating this idea into cosmology demands careful calibration to align with observational data, much like fine-tuning a cosmic radio to catch the correct signal. One such model marries the idea of variable constants with tired light to posit a universe that is 267 billion years old. According to this view, the early cosmos operated under different physical laws that permitted swift galaxy formation. While tired light accounts for the redshift we see today, without needing universal expansion, the supporting mathematics is sophisticated but highly debated. Detractors point out that altering fundamental constants would have cascading effects on many other observable phenomena, from the cosmic microwave background to the creation of light elements in the early universe. The theory would have to explain how these changes happened in just the right way to align with all current observations. Proponents argue that our present understanding of physics is incomplete and that Webb's findings prove the need for new theoretical models. They note that the standard cosmological model already relies on the mysterious concepts of dark matter and dark energy to fit observations, making variable constants a potentially equally plausible idea. The argument over inconstant constants touches upon a more profound question regarding the nature of scientific truth. Are the laws of physics genuinely universal and eternal, or do they evolve with the cosmos they describe? As scientists wrestle with these philosophical questions, the galaxies uncovered by Webb continue to challenge our most fundamental assumptions about reality. Confronted with observations that appear to defy the laws of physics, astronomers have employed their most formidable tool: computer simulations capable of modeling the birth and development of galaxies across cosmic history. These digital universes were intended to either validate the impossibility of early massive galaxies or show how nature could have accomplished what seemed unachievable. The initial simulations offered a bleak outlook. Using standard physics and established galaxy formation models, no computer could generate the massive early galaxies that Webb had found. The simulations repeatedly yielded small, undeveloped systems that looked nothing like the cosmic titans observed in the distant universe. But as scientists refined their models and explored different possibilities, a striking new idea came to light. What if the early universe underwent short, incredibly powerful bursts of star formation, like cosmic explosions of creativity that condensed millions of years of development into mere geological moments? These starbursts, events could happen when galaxies crashed and merged, funneling immense quantities of gas toward their centers. The subsequent gravitational squeeze would set off waves of star formation far more powerful than anything observed in the contemporary universe. For short durations, galaxies could convert almost all of their gas into stars with remarkable efficiency. The simulations demonstrated that such intense episodes could produce bright, massive-looking galaxies without necessarily having as much stellar mass as first believed. A galaxy in the throes of an extreme starburst might seem to hold hundreds of billions of stars, while its actual mass was considerably less. This insight provided a potential link between observation and theory. The early universe might have been a much more chaotic and dynamic environment than we assumed, with regular galaxy collisions and powerful starbursts creating the appearance of impossible maturity. Computer models also showed that cosmic dust was instrumental in making early galaxies look red and large. Young, hot stars generate dust that absorbs blue light and re-emits it in the infrared spectrum. This effect could make a relatively modest galaxy appear both red and massive when viewed through Webb's infrared detectors. The simulations hinted that the universe might not have to break its own rules to form the galaxies we see. It might just operate under more extreme conditions than we had ever conceived. Hidden within the static of radio frequencies is the very echo of creation, the cosmic microwave background radiation, which bathes every corner of space in the faint warmth of the Big Bang. This ancient light, let loose when a universe was just 380,000 years old, stands as our most direct proof of the expanding universe model. The cosmic microwave background is almost perfectly even across the entire sky, with minute temperature differences that align with the predictions of Big Bang cosmology with astounding accuracy. These small variations are the seeds that eventually blossomed into galaxies and galactic clusters, like ripples on a cosmic lake that spread out over billions of years. However, the tired light theory struggles to explain this radiation. In an expanding universe, the cosmic microwave background naturally cools as space expands, preserving the precise blackbody spectrum we measure. In a static universe, this same radiation would have to be generated and sustained by some undiscovered mechanism. Advocates of tired light have put forward several potential solutions to this issue. Some theorize that the cosmic microwave background is the collective starlight from all galaxies throughout time, redshifted by tired light processes until it appears as microwave energy. Others suggest the radiation is a result of interactions between photons and the cosmic medium itself. Recent studies have tried to model how a tired light universe could create the observed cosmic microwave background. While these models demand careful tuning of unknown physical processes, they show that alternative explanations, though more intricate than the expanding universe model, are not entirely out of the question. The cosmic microwave background also offers insights into the early universe's composition and history. Its near-perfect uniformity indicates that the primordial cosmos was incredibly smooth, with only tiny density fluctuations that grew over time into the structures we see today. This smoothness itself presents difficulties for both expanding and static universe models. How did the early universe become so remarkably uniform? Why do we measure the same temperature in regions that should never have been in causal contact? These questions point to deeper puzzles about the very nature of space and time. As astronomers continue to chart the cosmic microwave background with ever-increasing precision, this ancient reverberation of creation remains a crucial piece of evidence in the ongoing trial of cosmological theories. In the prevailing cosmological model, dark matter constitutes 85% of all matter in the universe, forming the gravitational framework on which galaxies and galaxy clusters are built. This unseen substance is detected only through its gravitational influence, which bends light and affects the movement of visible matter. The massive early galaxies found by Webb present a major hurdle for dark matter theories. These galaxies seem to have formed inside dark matter halos, invisible gravitational wells that attract and contain ordinary matter. However, constructing such massive halos so early in cosmic time demands processes that stretch the limits of current dark matter models. Computer simulations indicate that the largest dark matter halos in the early universe should have been relatively small and uncommon. They would require billions of years of mergers and accretion to develop into the massive structures needed to host giant galaxies. The sudden appearance of these systems implies that either dark matter behaves differently than we believe or that our models are missing some fundamental physics. Some scientists suggest that dark matter might have been more concentrated in the early universe, which would have allowed for quicker halo formation. Others propose that dark matter could interact with itself in ways that speed up structure formation beyond what current predictions allow. These adjustments would necessitate significant changes to our understanding of this enigmatic substance. The tired light alternative provides a different angle on the dark matter puzzle. If the universe is much older than currently thought, dark matter halos would have had more time to grow to enormous sizes. The apparent youth of distant galaxies would be an illusion created by tired light effects, while their actual age would be billions of years greater. This scenario could potentially account for why early galaxies look so massive and well-developed. In a universe that is 26 billion years old instead of 14 billion, Even the most remote galaxies would have had plenty of time to gather the dark matter required for their formation. However, alternative cosmologies still need to explain all the other evidence for dark matter. From galaxy rotation curves to gravitational lensing, the dark matter issue shows how altering one piece of the cosmological puzzle can have wide-ranging effects on our understanding of the universe's unseen components. As scientists persist in their search for dark matter particles and study their influence, the early galaxy discoveries add a new sense of urgency to solving this cosmic puzzle. The most distant galaxy merger ever witnessed tells a tale of cosmic ferocity that defies our understanding of the universe's development. Situated 13 billion light-years from us, this ancient collision captures two massive galaxies in the act of merging into an even larger entity. Galaxy mergers are among the most dramatic phenomena in the cosmos, akin to celestial traffic accidents that play out over hundreds of millions of years. When two galaxies collide, their combined gravity warps both systems, pulling out long filaments of stars that span millions of light-years. The central black holes at their cores spiral toward each other, eventually merging in a final cataclysmic release of gravitational waves. But this specific merger introduces a timing issue that reflects the larger crisis in cosmology. The two galaxies involved are already enormous and mature, with billions of stars and sophisticated structures. The notion that such systems could exist and collide when the universe was merely 500 million years old seems nearly impossible. The merger also offers surprising insights into star formation in the early universe. The colliding galaxies exhibit evidence of powerful stellar nurseries, areas where new stars are being born at rates that dwarf anything seen in the modern cosmos. This hints that galactic interactions might have been more frequent and more intense in the primordial universe. Computer simulations of the merger indicate that the resulting combined system would have a mass comparable to our own Milky Way. Yet our galaxy needed more than 13 billion years to grow to its current size through countless smaller mergers and consistent star formation. How did the early universe achieve a similar outcome in a fraction of time? The merger also offers clues about the influence of supermassive black holes on galaxy evolution. Both galaxies show signs of actively feeding black holes at their centers, suggesting that these cosmic behemoths were instrumental in governing star formation and galaxy growth throughout cosmic history. As astronomers examine this ancient collision with unprecedented clarity, it's becoming apparent that the early universe was a far more turbulent and violent environment than once believed. The chaotic mergers of the primordial cosmos might contain the answer to how massive galaxies formed so quickly. This cosmic collision, preserved in light for 13 billion years, continues to challenge our beliefs about the tranquil evolution of the early universe. The definitive proof for any astronomical finding comes from spectroscopy, a method that separates light into its constituent wavelengths to reveal the chemical makeup, temperature, and motion of remote objects. When astronomers aimed their spectroscopic instruments at the impossible early galaxies, they were hoping for evidence that would either validate or dismiss the growing crisis in cosmology. The spectroscopic data presented a multifaceted story. Some of the galaxies that seemed massive in the initial photos were revealed to be distant quasars, supermassive black holes shining with such intensity that they overshadowed their host galaxies. These cosmic beacons produced the illusion of immense stellar mass, when in fact the phenomenon was driven by black hole activity. However, many other galaxies passed the spectroscopic examination with distinction. They displayed clear evidence of large stellar populations, intricate chemical compositions, and the spectral characteristics of mature galactic systems. These were not optical tricks or cases of mistaken identity. They were genuinely massive galaxies that existed in the early universe. The chemical analysis provided especially startling findings. These early galaxies possessed considerable quantities of heavy elements like carbon, oxygen, and iron, elements that should have been scarce in the primordial cosmos. The presence of these materials indicated that several generations of stars had already completed their life cycles, scattering their nuclear byproducts across space. This process of chemical enrichment typically requires billions of years. In the contemporary universe, we can observe the slow buildup of heavy elements as successive stellar generations contribute to this cosmic recycling. Yet these early galaxies appear to have condensed this entire timeline into just a few 100 million years. The spectroscopic analysis also verified that these galaxies were indeed at the vast distances first estimated. Their light had journeyed for 13 billion years to reach us, confirming that we were seeing them as they were when the universe was truly young. This eliminated the chance that they were closer objects masquerading as distant ones. Perhaps most importantly, the spectroscopic data showed that these early galaxies were not only large but also incredibly varied. Some exhibited signs of vigorous star formation, while others seemed to have already ceased creating new stars. This diversity pointed to a rich ecosystem of galaxy types that challenged existing models of early cosmic evolution. The spectroscopic findings left astronomers with a firm conclusion. The early universe had indeed produced massive, mature galaxies in an astonishingly short amount of time. Long before the James Webb Telescope unveiled its impossible galaxies, scientists were aware that the early universe experienced a profound change known as reionization. This event, which took place about 1 billion years after the Big Bang, involved the first stars and galaxies burning through the neutral hydrogen that permeated space, resulting in the transparent cosmos we see today. The massive early galaxies found by Webb were key players in this cosmic upheaval. Their powerful star formation and supermassive black holes generated enough high-energy radiation to ionize huge swathes of space around them. These galaxies were not just setting records for their size. They were actively reshaping the universe itself. Computer models of reionization had suggested a gradual process, with numerous small galaxies slowly clearing the cosmic haze over hundreds of millions of years. But the existence of massive early galaxies indicates that reionization might have been more forceful and swift than previously imagined. The consequences reach well beyond galaxy formation. If reionization happened more quickly than anticipated, it would influence the formation of the first stars, the growth of supermassive black holes, and the overall development of cosmic structure. The entire schedule of early universe evolution might need to be squeezed into a shorter time frame. Recent observations of the cosmic microwave background offer further support for rapid reionization. The polarization patterns in this ancient radiation hint that reionization started earlier and unfolded more quickly than standard models suggest. This independent verification reinforces the idea that the early universe was more active and dynamic than once believed. The reionization event also helps explain why these early galaxies appear so red in Webb's images. The intense radiation from their stars and black holes heated the surrounding intergalactic medium, creating conditions that preferentially scatter blue light while letting red light pass through. This could make galaxies look redder and more mature than they actually are. As astronomers continue to investigate reionization through direct observation and computer simulations, the process is emerging as a critical link between the impossible early galaxies and the broader evolution of the cosmos. The reionization revolution altered not only the universe's appearance, but also our understanding of how quickly cosmic evolution can unfold under extreme conditions. As the body of evidence for impossible early galaxies grew, a small but expanding contingent of scientists began to wonder if the issue wasn't with galaxy formation, but with our core assumptions about the universe itself. Perhaps the Big Bang model, for all its achievements, was missing a vital piece of the puzzle regarding space, time, and cosmic history. Alternative cosmologies had long existed on the scientific fringes, but Webb's discoveries endowed them with new significance and urgency. These models offered fundamentally different interpretations for the observations that underpin modern cosmology, from the cosmic microwave background to the expansion of space. One category of alternatives propose that the universe might be cyclical rather than linear, undergoing endless periods of expansion and contraction in an eternal cosmic rhythm. In such frameworks, the current expansion phase could have been preceded by innumerable previous cycles, each contributing to the structures we see today. This would offer almost infinite time for galaxy formation and evolution. Other models suggest our universe might be situated within a higher dimensional space governed by physical laws that differ from those we experience locally. These extra dimensions could offer additional sources of energy and matter, accelerating galaxy formation beyond the constraints of four-dimensional physics. The steady-state cosmology, once a major competitor to the Big Bang model, also saw a resurgence. Modern iterations of this theory sought to explain the cosmic microwave background and other phenomena, while asserting that the universe has always existed in a state similar to its present one. In such models, the apparent evolution of galaxies with distance could be attributed to tired light or other redshift mechanisms. Most compellingly, some researchers propose that the universe might have gone through periods of modified physics, where fundamental constants and forces had different values than they do now. These variable constant models could account for rapid early galaxy formation while remaining consistent with other cosmological observations. Each alternative cosmology had to overcome significant hurdles to explain the full spectrum of astronomical data. But Webb's findings showed that even the standard model was struggling to account for all the evidence. The dilemma in cosmology has unlocked possibilities that were considered inconceivable only a short time ago. As scientists investigated these alternative frameworks, they found themselves confronting profound questions about the nature of scientific truth and the boundaries of human knowledge about the cosmos. Contained within the breathtaking images of early galaxies is a more subtle but equally vital narrative written in dust and gas, the fundamental ingredients from which all stars are made. The Webb telescope's infrared capabilities have revealed not just the galaxies themselves, but also the intricate chemistry and physics of their stellar nurseries. Dust particles, despite their small size, have a disproportionately large impact on galaxy evolution. These microscopic grains absorb starlight and re-emit it as infrared radiation, warming the interstellar medium and influencing how new stars are born. In the early universe, dust should have been scarce, as it is primarily formed in the atmospheres of dying stars and supernova remnants. Yet the massive early galaxies found by Webb harbor surprisingly large quantities of dust for their presumed age. This dust indicates that numerous generations of stars had already lived and died, adding their remnants to the cosmic recycling system. The high abundance of dust in such young galaxies suggests that stellar evolution occurred much more rapidly than current models allow. The gas dynamics within these galaxies also offer clues about their formation. High-resolution spectroscopy reveals gas flowing into the galactic centers at incredible rates, fueling both star formation and the growth of central black holes. These inflow rates are far greater than anything seen in the contemporary universe, suggesting that early galaxies operated under different physical conditions. Computer simulations of gas dynamics in the early universe indicate that the higher density and temperature of the primordial cosmos might have facilitated more efficient gas cooling and star formation. The denser environment of the early universe could have compressed gas clouds more effectively, initiating star formation at rates that are impossible in today's more rarefied cosmos. The observations of dust and gas also provide clues about galaxy mergers and interactions. Many early galaxies exhibit disturbed gas kinematics, indicating that they are either in the process of merging or have recently undergone major collisions. This violent setting could explain their swift assembly and immense scale. As astronomers continue to examine the dust and gas content of early galaxies, they are finding evidence of a universe that was more chemically developed and dynamically active than previously thought. These microscopic particles and invisible gases are key to understanding how the cosmos transformed from simplicity to complexity in record time. The dynamics of dust and gas portray an early universe that was not just young, but fundamentally different from the one we observe today. Nature has given astronomers a cosmic magnifying tool in the form of gravitational lensing, the bending of light by massive objects, which can amplify and warp the appearance of distant galaxies. Some of the most stunning discoveries of early galaxies have been aided by this natural telescope. However, this effect also complicates our efforts to understand their true characteristics. When light from a distant galaxy travels near a massive galaxy cluster, the cluster's gravity functions like a lens, bending and concentrating the light rays. This can make faint, distant galaxies appear much brighter and larger than they are in reality. For astronomers studying the early universe, gravitational lensing can unveil galaxies that would otherwise be too dim to see. But lensing also introduces a potential for misunderstanding. A galaxy that looks massive might actually be quite small, its light magnified by the intervening gravitational lens. To ascertain the true properties of lensed galaxies, careful modeling of the lensing effect and precise measurements of the light amplification are required. Some of the most remarkable early galaxy discoveries have been gravitationally lensed, which raises doubts about whether their apparent masses are genuine or inflated by the lensing phenomenon. Astronomers must meticulously account for the lensing amplification to determine the intrinsic properties of these remote systems. The lensing effect can also produce multiple images of the same galaxy, enabling astronomers to study different facets of a single object. These multiple images can offer details about a galaxy's structure, star formation rate, and chemical composition that would be unobtainable from a single image. Recent studies have utilized gravitational lensing to pinpoint some of the most distant galaxies ever seen, pushing the limits of the observable universe. These lensing-assisted findings show galaxies that existed just a few 100 million years after the Big Bang, during an epoch when the universe was still in its earliest stages. The magnifying power of gravitational lenses illustrates how the universe itself can act as a scientific instrument, using the curvature of space-time to reveal otherwise unseen cosmic structures. As astronomers refine their techniques for modeling and correcting lensing effects, these natural telescopes will continue to offer crucial insights into the early universe. The dynamic between gravitational lensing and early galaxy observations underscores the intricate relationship between observation and interpretation in modern astronomy. Every galaxy recounts the history of its creation through the collective light of billions of stars, each adding its unique spectral signature to the celestial symphony. Astronomers employ stellar population synthesis, the method of modeling how various combinations of stars generate the light we see, to decipher these galactic histories. The technique is akin to archaeological investigation, where scientists reconstruct the past from incomplete evidence. By examining a galaxy's colors, brightness, and spectral features, astronomers can estimate the number of stars it holds, the types of stars that are most common, and when its major episodes of star formation took place. For the massive early galaxies Webb has uncovered, stellar population synthesis presents a riddle within a mystery. These systems exhibit signs of both young and old stellar populations, hinting at complex formation histories that defy simple models of galaxy evolution. Some seem to have created most of their stars in powerful bursts, while others show evidence of a more gradual accumulation. The existence of red giant stars in these early galaxies is especially startling. Red giants are evolved stars that have used up their hydrogen fuel and swelled to immense proportions. The presence of these stars suggests that the galaxies must have been forming stars for hundreds of millions of years before the time at which we observe them. Patterns of chemical abundance offer further clues about stellar evolution in the early universe. The ratio of different elements in a galaxy's stars chronicles the history of nucleosynthesis, the process by which stars forge heavy elements and release them into space upon their death. Early galaxies display surprisingly high levels of elements like oxygen and iron, indicating rapid chemical development. Stellar population synthesis also points to top-heavy initial mass functions, meaning a greater proportion of massive stars than is seen in the local universe. Massive stars have short, brilliant lives and produce more heavy elements per unit mass than their smaller counterparts. This could explain how early galaxies achieved such swift chemical enrichment. Computer models of stellar population synthesis must consider the different physical conditions of the early universe, including higher gas densities, altered radiation fields, and different cooling mechanisms. These environmental factors could have a significant impact on how stars form and evolve. As astronomers enhance their stellar population synthesis models, they're finding evidence of a universe where star formation and stellar evolution operated under conditions very different from what we see today. The mounting evidence from the James Webb Space Telescope has reached a point where individual puzzles have merged into a systematic challenge to our very understanding of the universe. What started as astonishing findings about early galaxies has now become a fundamental inquiry into the nature of cosmic evolution itself. This paradigm shift reaches beyond astronomy and into the philosophy of science. The Webb discoveries illustrate how rapidly established scientific theories can be questioned by new data, serving as a reminder that our comprehension of the universe is always temporary and open to change. The crisis in cosmology is a reflection of the healthy skepticism that fuels scientific advancement. Several competing theories have arisen to explain the impossible early galaxies. Some scientists favor modified galaxy formation physics, suggesting that star formation and black hole growth were much faster in the early universe than current models allow. Others support alternative cosmologies that offer more time for galaxy creation by altering our understanding of space and time. This debate has divided the astronomical community, with each faction advocating for its preferred interpretation of the data. Scientific conferences and research papers now commonly feature discussions on the early galaxy problem, with researchers suggesting increasingly inventive solutions to bridge the gap between observation and theory. This paradigm shift also mirrors broader transformations in the practice of astronomy. The Webb telescope marks a significant advancement in observational power, permitting astronomers to study the early universe with unprecedented clarity. This technological leap has uncovered phenomena that were invisible to previous generations of telescopes. As more data streams in from Webb and other sophisticated instruments, this paradigm shift is likely to gain momentum. Every new observation holds the potential to either bolster the case for alternative cosmologies or unveil new aspects of galaxy formation that could reconcile observation with theory. The paradigm shift in cosmology reminds us that science is not a static collection of facts, but a vibrant process of discovery and revision. The impossible early galaxies have compelled astronomers to face the boundaries of their knowledge and entertain possibilities that seemed absurd just a few years ago. History will determine whether this paradigm shift results in a complete revolution in our understanding of the universe or a mere refinement of existing theories. As we find ourselves on the brink of a new cosmological era, the James Webb Space Telescope has offered us a view of a universe far more bizarre and intricate than we had ever conceived. The impossible early galaxies that ignited this crisis have forced us to address fundamental questions about the very nature of space, time, and cosmic history. The evidence suggests a universe where the laws of physics may have operated differently in the remote past, where galaxy formation occurred at an astonishing pace, and where the timeline of cosmic evolution might need to be completely rewritten. Whether these findings will ultimately validate alternative cosmologies like tired light or prompt modifications to the Big Bang model is yet to be determined. What is certain is that the universe resists being neatly categorized by our expectations. The massive early galaxies, the rapid emergence of supermassive black holes, the accelerated rate of chemical evolution, all of these phenomena challenge our most fundamental assumptions about how the cosmos functions. They serve as a reminder that, despite centuries of scientific advancement, we still have a great deal to learn about the universe we call home. The Webb telescope has only just started its journey of exploration. As it continues to probe deeper into space and further back in time, It will undoubtedly uncover more surprises that challenge our understanding of cosmic history. Each new finding could either exacerbate the crisis in cosmology or lead to revolutionary new insights into the nature of reality itself. The narrative of the impossible early galaxies is still being written. Future observations will decide whether these celestial titans represent a deep flaw in our comprehension of the universe or simply the first look at a more complex and fascinating cosmos than we ever dared to imagine. As we persist in exploring the profound mysteries of space and time, we are reminded that the universe is not only stranger than we think, it is stranger than we can think. The James Webb Space Telescope has initiated a new chapter in humanity's quest to find its place in the cosmos. And the forthcoming revelations may be even more astonishing than the discoveries that have brought us to this point. The impossible has become a reality, and the universe will never appear the same again. The James Webb Space Telescope has shown that the universe is not the systematic, foreseeable place we once thought it was. From the instant astronomers first saw those impossible red dots shining in the cosmic dawn, we have had to face the idea that everything we believed about the universe's origin could be incorrect. These ancient galaxies, enormous and fully formed when the cosmos was supposedly in its infancy, have shaken our faith in the Big Bang Theory and created an opening for groundbreaking new concepts about space, time, and the very fabric of reality. The evidence is irrefutable. Galaxies that should not be there are scattered throughout the early universe like cosmic testaments to our own limitations. Whether they were created through impossible physics, inhabit a universe far older than we assumed, or signal the need for entirely new cosmological frameworks, these discoveries have profoundly altered our understanding of the cosmos. As we continue to delve into the deepest puzzles of space and time, we are on the verge of a new scientific revolution. The impossible early galaxies might be just the start of a total transformation in how we perceive our position in the universe. The next discoveries are waiting, and they are likely to be even more remarkable than the revelations that have led us here. The cosmos is beckoning, and we are finally prepared to respond.